Particle Physics 2011, question 10a. So in this first question here, we can see as always that we need to break down our question into our parts before we start the question so that we don't miss any of our questions. So I'm going to call them part 1, which is listing 3 quantities. Part 2, writing an equation. Part 3, what's the contradiction? Part 4, which is listing the fundamental forces. Part 5, which fundamental force? Part 6, why are there new particles? Part 7, write an equation. And part 8, show our kinetic energy. Okay, so you can see there's quite a few steps here in this question. And if you're under time pressure, it's always very easy to miss one of these. So the best thing to always do in physics is when you're doing your question is number them so you can refer to them in your question, and also then tick them as you've done them so you don't miss any parts in the exam. Okay, so let's look at question 10a, part 1. So we have to list 3 quantities that are conserved in nuclear reactions. So what is conserved? Well, the 3 obvious ones that we generally will always go with are your momentum is conserved. We always have our charge must be conserved. And of course our mass energy is conserved. They're the 3 main ones that you'll always kind of learn. But of course we have angular momentum must be conserved. We've got the number of nucleons must be conserved, obviously in terms of protons and neutrons. So there's quite a few, but you know these are 3 main ones that we deal with at leaving cert level. So the next one then is we have to write an equation for a nucleus undergoing beta decay. So it doesn't actually state what nucleus is undergoing beta decay. So when we don't know what nucleus it is, we generally just call it the letter X. So in general, we would say our element is going to decay into a new nucleus where the mass number will stay the same and the atomic number will increase by 1 because when we emit a beta particle, its mass number is 0 and its atomic number is -1. So of course we could do an example. So we could have radium 228, 88. And of course if we have a beta particle emitted, you could also write electron 0 - 1. So we can use that to represent our beta particle either. And of course what will it decay into? So again, you would go to your maths tables, page 79, and we would always identify our radioactive decay. Our new elements are always identified by their atomic number. So therefore the atomic number is going to increase by 1 to 89 and the mass number stays the same. So remember the mass number, most of these radioactive decay elements, they're isotopes. So you'd never be able to identify the isotopes from the periodic table of elements. So we're only ever identifying by the atomic number, so by the 88 and the 89. So if we go to page 79 in our maths tables, what we can see then is 89 would be actinium. Okay. You could of course have neutron. Again, your beta. Or you could say electron. And we'd have the proton 1 and +1. So again, all of these are examples of a nucleus undergoing beta decay. Okay, so our marks for the first one there. So any 3 valid answers, we had 2 marks for each of those. And then for writing the equation, we had 9 marks. So it was 3, 3 and 3 for that question. So in other words, you had to have 3 parts to your equation. So you had the nucleus decaying and the beta particle being emitted. So that's how you were being broken down. So let me just erase that there. Okay, so the third part of the question says, in initial observations of beta decay, not all three quantities appeared to be conserved. So what is the solution for this contradiction? Well, it was, of course, the proposal for the neutrino. So it was, of course, the proposal of the neutrino. Sorry, just change to blue. It says the proposal of the neutrino. So it was in 1931 that Pauli proposed that some sort of a particle must be emitted and carrying away its missing energy and momentum. And obviously Fermi then named it the neutrino. But it was this neutrino that was causing the contradictions in the calculations. Okay, so part 4 then, we can see here that we have to list the fundamental forces, and really important here that it's in increasing order of their strength. So of course we could be asked to compare the fundamental forces of nature based on their strength, what they act on, their occurrence, or even their range. So we have to be able to put them in order increasing or decreasing. So here if it's in order of increasing strength, then which is the weakest? Well, gravitational force is the weakest. Gravitational. Followed by the weak nuclear force. Followed by electromagnetic, and of course the strongest is the strong nuclear, hence the name. Stating the obvious in science a lot of the time. Okay, so we have 9 marks going for this. So again, that's broken down into 3 parts. So if you've named any 2 correctly, we'd get 3. Then if we have named 4 correctly, we get 6 marks. And of course, then if we have the correct order, we get those last 3 marks. Okay, so for part 5, we have to state which fundamental force of nature then is involved in beta decay. Well, of course, it's beta decay, and it is the weak nuclear force. Okay, so then again for the weak nuclear force we were getting 3 marks for that. Alright, so the next part of the question says, in the Large Hadron Collider, the LHC, we have 2 protons and they have the same energy, so the same kinetic energy, travelling in opposite directions, and they collide. So when we have the 2 protons colliding, what we end up with is the 2 protons are going to remain after the collision, but we have then 2 charged pi mesons are produced. So the first thing they want us to state is, well, why are new particles produced in the collision? Well, why are they produced? Well, we know that the energy that the protons have in their collision are going to be converted into mass. Well, why? Well, it's our E equals mc squared. So energy is converted into mass. So we have our mass energy conserved. And of course you could state, well, that's our E equals mc squared. Okay, so again we have 3 marks for that. So obviously the more energy these colliding particles have, the greater the variety of the particles that are going to be produced after the collision. And this is why obviously with the Large Hadron Collider they keep trying to increase their speeds, make modifications and improving. So hopefully in 2021 we'll have even greater variety and getting closer to our understanding of the origins of the universe with all of this energy. Okay, so the next part then, if we go back, says write an equation then to represent the collision. Okay, so we have 2 protons beforehand, and then after the collision we also have 2 protons. Now we have to be careful here because it says we have 2 charged pi mesons. So the fact that they're charged means that it's definitely not going to be the neutral pion. And if we look beforehand, well, we have +1 for our charge of the proton, +1 for the charge of the proton, +1 for the charge of the proton, and +1 for the charge of the proton. So therefore we have a total of a charge of 2+ on the left and 2+ on the right. And now we know by our laws of conservation, it was one of the questions that was asked at the start, the very first question. So therefore we have to make sure that our charge before and after is the same. So therefore we could have neutral pions here, and we could have countless amounts of neutral pions, because if there was a small amount of energy, we'd have 1. If we have more energy, we could have 2. More energy, we could have 3 or 4. So we'd have more and more energy allows for more and more mass because of our conservation of mass. But here, because we're told that they are charged, well, I can't have a positive pion and another positive pion, because then that would give me an excess of 2+ on the right hand side of my equation. So that implies that it has to be opposite charged pions. So in other words, we have a charge of +1 for the plus pion, and we have a negative charge for the negative pion, and therefore their charges cancel out. That would be 0. Okay, so really important to watch for that in these equations when we're doing our particle collisions or the proton collisions. So again, we were getting 9 marks in total for this equation. So we have 3 marks for showing our 2 protons before and after. And then we have, so for this bit here, we were getting 3 marks. And then we had 3 marks for showing the 2 pions. So again, 3 marks for the 2 pions. And then, of course, we have 3 marks for the correct format. So in other words, our charge would be the important thing there as well for our pions. Okay. So if we're looking then at the next part of the question, so part 8, and let's go back and see there. Well, we have now to show that the kinetic energy of each incident proton must be at least 140 mega electron volts for the collision to occur. So of course we have to make sure that we're looking at electron volts here in the question, and again we're looking at the mass of, or the energy of each incident proton. Okay, so keyword here is that it says at least, right? So at least implies that it is going to be enough energy. This is the minimum energy required to make the 2 pions. Okay, so if we had more energy, then what would that energy be used for? Well, if we've just made our 2 pions, then we would have excess energy, and that would be used as kinetic energy. Okay, so here we're literally just making the pions. So therefore, our energy required to make the pions is going to be found by using our E equals mc squared. So what is the mass of our pions? Well, again, if we want to know what the mass of our pion is, well, if we go to our tables, which is page 48 in our maths tables, what you can see is the positive pion and the negative pion, okay, have a relative mass of 273. Now, the relative mass is relative to the mass of the electron. And what's the mass of the electron? Well, the mass of the electron is on page 46 of our maths tables. And if we look at that, well, that's going to be 273 times, just let me remove that actually, I won't have space. So the mass of our electron then is, so 9.1093826 by 10 to the power of minus 31. So again, using every number on our maths tables if we're not given the values at the end of the question. So what is the mass of the pions then? If we multiply those out, well, that is 2.48686145 by 10 to the power of minus 28, and that's kilograms. Now again, we have to obviously be careful there, because as I said earlier, the fact that we had deciphered from the question that it was a positive pion and a negative pion If it was a neutral pion, it has a different relative mass. It has a relative mass of 264 with respect to the mass of the electron. So always make sure, as I said, you're reading page 48 of your maths tables and that you're clearly identifying what is the relative mass for the question. Okay, so now we know the mass of our pions. If we're looking at the energy needed to make them, well, we have 2 of these pions, so we have to double that mass. Okay, so we have 2 of our pions, and then that's times speed of light squared. So again, speed of light wasn't given to us, so we're going to take from our tables. So 2.99792458 by 10 to the power of 8 and squared. So that is page 47 there for C. And then if we multiply that out, what do we get for our energy? So that is 4.470159214 by 10 to the power of minus 11, and that's joules. So basically this is the energy needed to make the 2 pions. Okay, so what do we need to look at, and how are we going to use this? Well, if this is the energy needed to make the pions, well, basically this is the energy of the 2 colliding protons up here in this equation up here. So their energy is going to be used for the energy here to make that those 2 pions, okay? So we need to first of all change that into electron volts. So to get into our electron volts, we again need to go to page 46 of our maths tables. And therefore we're going to take that energy, which is 4.44701592214 by 10 to the power of minus 11. And we're going to then divide that by the charge on the electrons. So our electron volt 1.602176653 by 10 to the power of minus 19. And therefore, if I divide that, that gives me 2.79005 for 111, I should say, by 10 to the power of minus 30. And that's electron volts. And then I need to change that to a mega electron volts. Sorry, I was thinking that number looked a bit strange. I was like, that's not possible. So obviously I put in plus 19 there into my calculator. So that when we divide those two, we actually get 279,054,1111. Okay, electron volts. And of course we need to write that as mega electron volts. So if we move our decimal place back 6 places, well, that gives me 279 mega electron volts. And therefore, what can we say? Well, that is the minimum energy needed to make the 2 pions. So in other words, the kinetic energy of the 2 colliding protons must be 279 mega electron volts. But again, if we go back to the question there, it says show that the kinetic energy of each incident proton must be at least 140 mega electron volts. Okay, so if I divide that by 2, well, again, if I divide this whole number up here by 2, I end up with 139.5 mega electron volts, which is of course 140 mega electron volts. So of course I shouldn't really be rounding there until the end, because if I divide 279 by 2, I'll still get 139.5. Okay, so what were our marks for that calculation? So we had to get the mass of our pions first, which was 3 marks. Using our E equals mc squared formula was 3 marks. For getting out the energy required to make the 2 pions was 3 marks. And then for getting the minimum energy needed to make the 2 pions, we were getting our 3 marks. So here. And then, of course, dividing it by 2 to get the energy per proton was 2 marks. Okay?